Hello everyone. In this video, we are going to discuss the concept of planar graph. So what is the meaning of planar graph? A planar graph that can be drawn on a plane so that no two edges are crossed each other at a non-vertex point. I'm repeating once again. A planar graph is a graph that can be drawn on a plane or a sphere so that no two edges are crossed with each other at a non-vertex point. That type of graph is called planar graph. Okay. For example, if I take planar graph with four vertices, just let us assume that I'm taking a graph of four vertices. Like this. Okay. Four vertices, we have six edges. Like A, B, C, D. So in this graph, if you observe, there are two edges which are crossed with each other. The first edge is BD, another one is AC. So AC and BD are crossed with each other, right? But in planar graph, no two edges are crossed with each other at non-vertex point. Therefore, we can modify this graph in such a way that it is converted into planar graph. Okay, observe how I'm going to modify this same graph. This graph also same as this is one edge. Okay, so we have like A, B, C, D, right? Now, instead of drawing BDH, in the original graph, okay, we can also draw the BDH like this, B to D, so that no two edges are crossed with each other at non-vertex point. Therefore, it is called planar graph. Okay. So, what is the definition of planar graph? The definition of planar graph is nothing but we can say a graph or a multigraph. A graph or multigraph a graph or a multigraph that can be drawn in a plane that can be drawn in a plane, okay, in a plane, so that no two edges crossed with each other cross each other is called a planar graph. Right? So this is the definition of planar graph. A graph or a multigraph that can be drawn in a plane so that no two edges cross each other is called planar graph. Okay. I'll take one more example to explain what is the meaning of planar graph. Okay. Suppose we have four vertices here. We take one more vertex, it will be A. Now A, B, C, D, E. Clearly, no two edges cross with each other. Therefore, it is called planar graph. Okay. Suppose if I add one more edge, yes, I can add one more edge like this from C to D. Still, it is a planar graph. Still, it is a planar graph because no two edges cross with each other. I can draw one more edge like C A to E. It is also planar graph. Okay, A to E. It is also planar graph. I can draw one more edge from A to D. A to D. It is also planar graph. Okay. Can I draw one more edge? One more edge. Suppose I can draw one more edge A to C also. Okay. Like that, we can draw edges. Okay. The basic idea is here, no two edges cross with each other. Okay, that type of graph is called planar graph. Let me give some example which are non-planar. Okay, which are non-planar. Suppose if I take the graph which is K5 graph. K5 is nothing but complete graph with 5 vertices. So the K5 graph structure is looking like this. We have 5 vertices. How many edges we have in K5? Number of edges in K5, 10 edges. Because number of edges in Kn is equals to n in 10 minus 1 by 2. Therefore, number of edges in K5 that equals to 10 edges. Up there, how I'm going to draw those 10 edges? So it is first edge, which is second edge, and then third edge, next fourth edge. So with respect to this vertex A, we created 4 edges. With respect to vertex A, we created 4 edges. Similarly, with respect to vertex B, let be B. So we want to create 4 edges. 1, then 2, next 3, and 1 edge already completed here. 1 edge already completed here, right? So 1 edge already completed. So this is these are the 4 edges drawn from B. Next, if I take C, like this C, so from C to A completed, C to B completed, we can take C to D, and then C to E. Okay. Similarly, D to E also completed. This is a graph which is K5 graph. Now this graph always non-planar. We cannot draw this graph such that no two edges cross with each other. Okay. So therefore, this graph is always non-planar graph. Okay. This graph is always non-planar graph. Okay. Let me check how can I say it is a non-planar graph by converting into some other shape. Suppose if I take vertices, same vertices like A, B, C, D, E. So first I can draw edge from A to B, and then A to D, A to C, and then A to E. So far no two edges cross with each other. Therefore I can say it is planar. Up to here it is planar. Next, when I start from B, obviously if I join B to C, it is crossing edge, right? Therefore I can join B to C like this. B to C. Similarly, I can join B to D. I can also join B to E. So far it is still plan graph only. Okay, so with respect to B, 4 edges completed. Now with respect to D, so D to E already over, D to B already over. Now I want to draw an edge from D to E, D to E. So D to E is also already over, right? Then how can I draw edge from D to C? Suppose if I draw edge from D to C, it is crossing it here, right? It is crossing. Then how can I draw edge? How can I draw edge? Okay, then is there any possibility of removing this edge and drawing in one more direction from A to E? Is it possible? Can we draw? Is it possible? No, right? Okay. So if I want to draw edge from D to C, D to C, only possibility is you have to remove this edge. But if I remove this edge we can draw from E to A. We can draw it from A to A. So is it possible to draw E to A? No, it is not possible to draw E to A. So therefore, this graph we cannot convert into planar. Okay, so therefore we can say it is non-planar graph. K5 is non-planar. K5 is non-planar graph. Okay, we can remove this diagram. So which is non-planar graph. K5 is non-planar graph. And let me take one more example. One more example. Let me take one more example like I'm taking 6 vertices like A, B, C, 6 vertices, D, E, F. Now quickly tell me what type of graph I'm going to draw. Obviously it is complete bipartite graph. Okay, complete bipartite graph. I want to verify is it planar graph or not. Let me check is it planar graph or not. So A to F we can draw an edge, A to E, then A to D. So far it is planar. If I start drawing graph, if I start drawing edge from B to D, still it is planar. So B to E, I want to draw edge from B to E. So of course I can draw edge from B to E in another direction. Okay. So let me draw in another. First, let me draw K33. You will get clear idea. So that is B to E and then B to F. Okay. Similarly, C to D and then C to E, C to F. This is called K33 graph. K33 graph. So this graph also we cannot draw such a way that no two edges cross with each other at non-vertex point. Therefore, it is non-planar graph. So K33 is non-planar. K33 is non-planar graph. Clear? So how many vertices are there in K5? Number of vertices in K5, obviously 5 vertices. 5 vertices. And how many edges we have? Number of edges in K5. So number of edges, obviously there are 10 edges are possible in K5. Right? So number of edges in K5, 10 edges. 10 edges. Similarly, number of vertices in K3. Number of vertices in K33. How many vertices we have? 3 plus 3, 6 vertices. Number of edges in K33. K33, 9 edges are there. Okay, 9 edges. So examination point of view, what kind of question they'll ask on based on this topic? So which of the following is a non-planar graph with minimum number of vertices? Which of the following is a non-planar graph with minimum number of vertices? So if they ask with the minimum number of vertices, then K5 is having only 5 vertices, which is non-planar graph. Okay, so let me write that point. Note a non-planar graph with minimum number of vertices. A non-planar graph with minimum number of vertices. What is that? That is K5. Okay. Similarly, if I ask with the minimum number of edges, so you can take its first note and the second note. A non-planar graph with the minimum number of edges is K33. This is a non-planar graph with minimum number of edges, K33. Right? Okay. So these are two important points regarding non-planar graphs. Please remember these 2 points. Next definition, I want to introduce one important definition that is called region. Region. What is the meaning of region? Region is nothing but a planar graph divides the plane into connected areas. A planar graph divides the area into connected areas. So those areas are called regions. For example, if I take previous example, which I have drawn earlier. So suppose if I take this example ABCD, it is a planar graph. This planar graph dividing the given plane into 3 regions. This planar graph divide the given plane into 3 regions. What are the regions? I can say it is region number 1 R1. It is region number 2 R2. Outside region is R3. Outside region is R3. Clear? The planar graph divide the given plane into regions. In this example, there are 3 regions are available. Okay. Let me take another example to get clear idea. Suppose if you take a planar graph with three vertices like A, B, C. So how many regions we have? Exactly, we have two regions. It is inside is R1, outside is we are having R2. Okay, R2. Right. Let me take another example. You'll get more clarity. You'll get more clarity. Okay. Suppose if I take one more example, like take one more example with four edges. With four edges. Let me call them as ABCD, like vertices ABCD. ABCD. And I'm taking one diagonal edge. Okay. One diagonal edge. So one more edge we can draw from A to C, right? We can draw one more edge from A to C. A to C. Now, how many regions we are having now? In this case, it is called region number 1. It is called region number 2. And it is called region number 3. It is called region number 3. So we are having three regions, and outside region we can call it as R4. Okay. Total we have four regions are available. Right? Total we have four regions are available. Now I hope you understood what is the meaning of region. Region is nothing but it is a bounded area which is occurred by planar graph. Okay, which is occurred by planar graph. For example, in this case, ABD. In first example, ABD is the region. Okay, and BCD is also region. So like that, in these three examples, we are having some regions, right? Okay. So you have to understand some important properties regarding regions. Properties of regions. Okay. See, if you observe in the first example, let me call it as example number 1. Okay, we have three examples. It's a first example, which is second example, example number 2, okay, and it is example number 3. Now we are talking about example number 1. Okay, in example number 1, I want to find degree of every region. Okay, I want to find degree of every region. Let me take, suppose in first example, in example 1, if I want to find degree of R1, how to find degree of any region? Degree of any region is nothing but number of edges bounding that region. Okay, clearly degree of R1 is equal to 3 because there are three edges are there. Let me draw those three edges now. It is first edge. It is first edge. It is first edge. It is second edge. It is third edge. Clear? There are three regions are there. Therefore, degree of R1 is equals to 3 here. Okay. In first example, degree of R1 is equals to 3. And what about degree of R2? Degree of R2, let me take in a different color, you can understand. How many edges are there now? Like 1, 2, 3 like this. There are three edges are available. Okay. So therefore R2 bounded by three edges, therefore degree of R2 is equals to 3. Degree of R2 is equal to 3. Okay. So degree of R2, we can say it is 3. So what about R3? What about R3? How many edges are exposed to R3? How many edges are exposed to R3? So clearly 1, 1, 1, 2, 2, and then 3, 4. So these are the edges are exposed to R3. That is called degree of R3. Okay, degree of R3. Is it clear? How many edges are exposed to R3? So 4 edges are there. Therefore, degree of R3 is equals to 4. So in example 1, okay, let me write this point now. Example 1. If I consider degree of R1, that equals to 3. Similarly, degree of R2 also 3. degree of R3, that is equals to 4, right? Degree of R3 is equal to 4. Next, if I take example 2, second example number 2, R1, how many edges are bounded for that region? 3 edges. Therefore, degree of R1 is equals to 3. What about degree of R2? How many edges are exposed to that region? Clearly, this edge is exposed to that region, right? Similarly, this edge also exposed to that region. This edge is exposed to that region. Clear? So how many edges are exposed to that region means 3 edges. Therefore, degree of R2 is equals to 3. Degree of R2 is equal to 3. Next, in example 3, what about degree of R1? Degree of R1, how many edges are enclosed in that region? 3 edges. Therefore, degree of R1 equal to 3. Right? What are the 3 edges? We can say like this. This is the first edge, right? It is the first edge, and it is second edge, and it is third edge. There are 3 edges enclosing R1. Similarly, degree of R2 is equals to again 3. And degree of R3 how many? So degree of R3 also 3, because number of edges bounded for the region R3 is equals to 3. Now I want to find degree of R4. Degree of R4. How many edges are exposed to R4? How many edges are exposed to R4? How many? Can you count them? How many of them are possible? How many edges are exposed to R4? Like this is the first edge which is exposed to R4. It is the second edge which is exposed to R4. It is the third edge which is exposed to R4. Therefore, degree of R4 is equals to, obviously here it is only 3. Degree of R4 is equal to 3. Clear? So that is a concept of degree of region. Degree of region. What did you understand from this? In a planar graph, the degree of any region is nothing but number of edges enclosing that region. This definition is valid if the region is bounded region. Okay. If the region is unbounded region, for example, in first example, who is unbounded region? R3 is unbounded region. If the region is unbounded region, then degree of unbounded region is equals to number of edges exposed to that region. Okay. So this total space R3, we are having total space. This total space, how many edges are exposed means 4 edges. Okay. So that is a concept of degree of region. Okay. There are 2 types of regions. One is bounded region, another one is unbounded region. Now, by using these examples, we can generate some properties of regions now. Okay. The first properties. First one, summation I runs from 1 to n degree of every region Ri must be equals to 2 times of total number of edges in the graph. It is same as sum degrees of vertices theorem. In sum degrees of vertices theorem, have you remembered? Let me write in the bracket. Sum degrees of vertices theorem, what did it say? Sum degree of vertices theorem. Sum of degrees of vertices. Sum of degrees of vertices theorem. It says that summation I runs from 1 to n degree of all vertices must be equals to 2 times of total number of edges in the graph. That is called sum of degrees of vertices theorem. Now here it is called sum of degrees of regions theorem. It is not vertices. It is regions theorem. Okay, it is called sum degrees of vertices theorem. It is called sum of degrees of regions theorem. Is it clear, everybody? This is the first property you have to remember. Means if you know some degrees of vertex theorem, you can easily understand some degrees of region theorem. Okay, what is the second property? Second property, have remembered in some degrees of vertex theorem, it clearly explained that if small delta of G denotes minimum degree of all vertices, small delta of G denotes minimum degree of all vertices, okay, and capital delta of G denotes maximum degree of all vertices, okay, maximum degree of all vertices, then must and should hold the relation is 2 times of number of edges by total number of vertices. Total number of vertices. This point I clearly explained in our previous videos. Okay, what is the meaning of the statement? It is called minimum degree. Please understand the minimum degree of all vertices. What is small delta of G? Minimum degree of all vertices. Minimum degree of all vertices. Whatever capital delta of G, it indicates that maximum degree of all vertices. Maximum degree of all vertices. Okay. Then whatever this 2e by total number of vertices, it is indicating average degree of vertices. Average degree of vertices. Okay. What is the formula for average degree of vertices? Average degree of vertices means total sum of the degree of all vertices by total number of vertices. Okay. So sum of the degree of all vertices must be equal to 2 times of edges. Therefore, I have written 2 times of edges, and the cardinality of E is nothing but total number of vertices. So it is called average degree. Please understand, it is called average degree. Okay. So this relation holds good in some degrees of vertices theorem. Now we can apply same concept here in some degrees of region theorem also. Okay. So what is that concept here? The concept is, suppose if the degree of each region is k, the second property, suppose if the degree of each region, the degree of each region is at least k, at least k means that is called minimum degree, right? Minimum degree, at least k, then it must and should satisfy the condition that minimum degree of region, small delta of R, okay, minimum degree of regions. Of course, here we cannot denote like this. Okay, let me write this one. If the degree of each region is at least k, then it must and should satisfy the condition k into number of vertices must be less than or equal to 2 times of number of edges. 2 times of number of edges. Okay. For example, if you see this, if you see the some degrees of vertex theorem, what is the minimum degree of all vertices here? Minimum degree of all vertices equals small delta of G. Therefore, here we can write it as small delta of G here we can write it as small delta of G into total number of vertices must be less than or equal to 2 times of number of edges less than or equals to capital delta of G into total number of vertices, right? Total number of vertices. We can write like this, means by taking cross multiplication. Now we can apply same concept here. See, what is small delta of G here? Minimum degree of all vertices. Suppose minimum degree of all vertices is at least k, then k into b equal to 2 times of edges, right? K into b equal to 2 times of edges. But here v is nothing but number of vertices. But now we are going to discuss this concept for regions. Therefore, it is true for number of vertices as well as it is also true for number of regions. Okay. So therefore, we can write it as in the place of v, we can write it as region, number of regions. Okay. Equal k into number of regions. K into number of regions must be less than 2 times of edges. Okay. If it is vertices, we can say cardinality of V. If it is region, we can say it is cardinality of R. Okay. Cardinality of R. Similarly, third property, if the degree of each region is at most k, that means it's a maximum degree, right? At most k means maximum degree. At most k, then it must and should satisfy the condition that k into number of regions must be greater than or equals to 2 times of number of edges. Like in this example, please observe here. Okay, so small capital delta of g is the maximum degree. Maximum degree into total number of vertices must be greater than or equal to 2 times of edges, right? 2 times of edges. The same way, k into r must be less than or equals to, must be greater than or equal to 2 times of edges. Now fourth property, suppose if the degree of each region is k, the degree of each region is k. Now by using some degrees of region theorem, if degree of each region is k, then how many regions we are having? R number of regions. Therefore, we can say k into number of regions must be equals to 2 times of number of edges. So why it is true? Because we know the condition. The condition is summation I runs from 1 to n. Degree of all regions must be equals to, degree of Ri must be equals to 2 times of number of edges. Degree of Ri must be equals to 2 times of number of edges. Clear? So it means that if you know the some degrees of vertices theorem, you can easily understand some degrees of region theorem. In the place of vertices, we can replace with only regions. Clear? So these 3 points are very much important. Okay. If you want, you can verify these 3 for the previous examples. Okay. Let me take simple example. We can verify them. I'm taking graph with 4 vertices. Like we have A, B, C, and then D. How many regions we have? We have 4 regions: R1, R2, R3, and outside we are having R1, right? In this case, what is the minimum degree of all regions? What is the minimum degree? Of course, minimum degree of all region is 3 only. 3. So how many regions we are having? 4 regions are there. Therefore, if minimum degree is k, right? If minimum degree is k, minimum degree of region is k, then it must and should satisfy the condition that k into total number of vertices or total number of regions, okay? K into total number of regions must be less than or equal to 2 times of number of edges. This is an important property which we covered, okay? Right here, what is the minimum degree of region now? Minimum degree of region is 3. Therefore, we can write it as, in this case, k is equal to 3. How many regions we are having? 4 regions. 3 into 4 less than or equal to 2 times of how many edges we have? 6 edges. 6 edges. Therefore, 12 less than or equals to 12, which is satisfied, right? Therefore, minimum degree of region is k, then k into r, k into number of regions must be less than 2 times of number of edges. Similarly, what is the maximum degree here? Maximum degree is equals to 4. Maximum degree of region equals to 4 because R4, sorry, maximum degree is also 3 because R4 is having how many edges are exposing to R4? 1, 2, 3, like this. Therefore, maximum degree also in this case 3. Okay, in this case 3. So therefore 3 into 4, 12. 12 greater than or equal to 12. Condition satisfied. In fact, in this case, degree of every region is 3. Therefore, 3 into 4 must be less than or equal, must be equal to total 2 times of edges, that equal 12. Let me take another example. We can verify it. Please look at this example. In the second example, what is the degree of R1? Degree of R1 is equals to 3. and degree of R2 also 3. So minimum is equals to maximum. Therefore, every region is having degree is k into v is equal to 2 times of edges. Obviously, if you take there are two regions and each region is having degree 3, therefore 2 into 3 is equals to total number of edges 2 into 3. That is 2 into 3 is equal to 2 times of number of edges. Therefore, this condition is satisfied. Okay? So you can verify for remaining also. Let me check it example 1. For example 1. So for example 1, let me check this condition. Summation I runs from 1 to n, degree of all regions must be equals to 2 times of number of edges. Okay, 2 times of number of edges. Let me check this one. So here degree of R1 is equal to 3, degree of R2 is equal to 3, degree of R3 is equals to 4. So if I sum up all these values, 3 plus 3, 6, 6 plus 4, 10. Okay. Therefore, this total summation, I'm getting value is equals to 10. Okay. This total summation value equal to 10. Whatever 2 times of number of edges, how many edges we are having in this graph? In example 1, 1, 2, 3, 4, 5, 5 edges, which is equivalent to exactly 2 times of 5. So, which is true. Which is true. What is the minimum degree of regions in this case? Minimum degree is equals to 3. Minimum degree is equal to 3. Okay. So therefore, let me check that condition also. At least k equal to here 3. At least k equal to 3. So at least k equal to 3 means it must satisfy the condition k into number of regions must be less than or equal to 2 times of number of edges. Okay. In this case, at least k means that is 3. How many regions we are having in example 1? In example 1, we are having 3 regions. So 3 into 4 less than or equal to how many edges? 2 times of 5 edges. Small correction. How many regions we are having? Only 3 regions, right? We have only 3 regions. Let's make it correct. So the number of regions in first example, 3 regions. Therefore, 3 into 3 less than or equals to 2 into 5, which is correct. 9 less than or equal to 10. This statement is correct. Similarly, in example 1, what is at most? At most means 4. At most degree means 4 because R3 is having degrees 4. Therefore, if I write the same statement, at most k is equals to 4. Now, according to that rule, it must satisfy the condition k into number of regions must be greater than or equals to 2 times of number of edges. Where k is nothing but here 4. Number of regions, we are having 3 regions. Greater than or equal to 2 into number of edges means 5. Therefore, 12 greater than or equals to 10, which is true, right? So therefore, we successfully proved the statement for example 1. Similarly, you can also verify it for example 2 and example 3. Okay. In fact, it is always true. In fact, it is always true. So these are important properties about planar graph. Okay. So we have one more property. That property based on the planar graph is Euler's formula, which is most important formula. Euler's formula. So what is Euler's formula? Euler's formula says that suppose if G is a connected planar graph, if G is a connected planar graph, if G is a connected planar graph, then it must and should satisfy the condition that number of vertices plus number of regions must be equals to number of edges plus 2. Okay, number of vertices plus number of region is equals to number of edges plus 2. This is called Euler's formula. You have to remember that proofs are beyond the scope of the GATE exam. Proofs are not required. Therefore, you have to remember the formula. Let me verify this formula for the problem. Like in this problem, let me take this as example. Okay. Let me take this example now. So for this example, I want to verify this condition. How many vertices are there in this example? We have 4 vertices. Therefore, number of vertices are 4. How many regions we have? 4 regions. Number of regions also 4. Number of edges, how many? 6 edges plus 2. Therefore 8 is equals to 8, which is satisfied. This is called Euler's formula. Okay, you have to remember this Euler's formula. I verified this by using this example. Okay, and this formula is working only for connected planar graph. Suppose if the graph is not connected planar graph, it is having some k components. But what in by components? So I will explain what is the meaning of component, connected component and disconnected components in continuity concept. Okay, but timing, you remember this point also. Suppose if G is a planar graph with k components, if G is a planar graph with k components, G is a planar graph with k components, then it must and should satisfy the condition number of vertices plus number of regions is equals to number of edges plus k plus 1. K plus 1. Okay, it means that it is having k components, therefore we can write it as k plus 1. Let me make it correct. K plus 1. Clear? This formula is known as Euler's formula for k components. K components. What is the meaning of component here? Actually, a graph is said to be connected graph if there exists a path between every pair of vertices. A graph is said to be connected graph if there exists a path between every pair of vertices. If the graph is not connected, it may contain connected components. Okay, it contains connected components. So what is connected components, and everything we'll discuss in continuity concept. But timing, you have to remember this point. Okay, let me check this problem, this formula, by taking simple example. Suppose I'm taking a graph. This is a graph which is having exactly 7 vertices. A, B, C, D, then E, F, G. E, F, G. There are 7 vertices are there. How many edges we are having? 1, 2, 3, 4, 5, 6, 7. 7 edges are there. 7 vertices and 7 edges. This is called planar graph. Planar graph with 2 components. Okay, 2 components are there. So G is a planar graph with 2 components. G is a planar graph with 2 components. K is equals to 2 components. 2 components. Now I want to verify whether the given formula is working properly or not for this graph. Okay, there are exactly 2 components. I want to verify this condition. Now in this formula, now how many vertices we are having? Number of vertices is equals to 7. Number of edges is equals to 7, and k equals to 2. But how many regions we are having? Number of regions. Can you calculate how many regions are there? One is R1 bounded by 4 edges. Another one is R2 bounded by 3 edges. Another one is R3, which is outside of all these. Therefore, only 3 regions are there. 3 regions are there. Okay, 3 regions are there. Now, in this case, number of vertices, just apply Euler formula. Euler formula says that number of vertices plus number of regions is equals to number of edges plus k plus 1. K plus 1. So here number of vertices are 7. Number of regions also 7. Number of edges, how many edges? 4 plus 3. Sorry for this. Regions are not 7, right? Sorry for the mistake. How many regions we are having? 3 regions. Number of edges, how many? 7. And k means 2 plus 1. So exactly 10 is equals to 10, which is satisfied. Okay. So G is a planar graph with 2 components, means we can write formula number of vertices plus number of regions must be equal to number of edges plus k plus 1. If the graph contains k connected components. Okay. Suppose the whole graph is connected, then k becomes 1. K becomes 1 means 1 plus 1 that equal to, that becomes Euler's formula. If graph is connected, k becomes 1. Once k becomes 1, then it becomes Taylor's formula, like which we already covered earlier. Okay, so you have to remember this formula, right? So this is a concept of planar graph. Okay, right. Thanks for watching this video.